Hello, and welcome to my talk on generalizing Alder's conjecture via a conjecture of Kang and Park. My name is Simran Khunger, and this work was done alongside my collaborators Adriana Duncan and Ryan Tamara, as well as our advisor Dr. Holly Swisher at the 2020 Oregon State REU. So to give you an overview of what we'll be talking about today, first we'll look at some background, including what an integer partition is, as well as the Kang and Park conjecture. We'll look at some project goals, some useful lemmas, the results from this research, and then finally some future directions. Great, so let's start with what a partition of n is. A partition of a positive integer n is a non-increasing sequence of positive integers such that those integers sum to n. And we're going to let the partitions of n, given a condition, be the number of partitions of n satisfying that certain condition. So let's look at a simple example. First, let n be equal to 4. Then the partitions of 4 are 1 plus 1 plus 1 plus 1, 2 plus 1 plus 1, 2 plus 2, 3 plus 1, and 4. And therefore we say that the partitions of 4, without any restrictions, is equal to 5. So an influential paper in our work was one by Kang and Park, where they introduced some important notation. So we're going to denote little q sub d a of n to be the number of partitions of n such that the parts have gap between them at least d, and the size of each part is at least a. Next, we're going to denote big Q sub db of n to be the number of partitions of n such that these parts come from the congruence classes plus or minus b mod d plus 3. And then finally, of most importance, we're going to define delta sub d ab of n to be the difference between qdA of n and qdb of n. And we're interested in the situation where a is equal to b. So that is delta sub dA of n, which we're going to define as delta sub dA of n. Great. So let's look at some important partition identities where this delta function has popped up in. First, you may have heard of Euler's identity, which says that the number of ways to partition n into odd parts is equal to the number of ways to partition n into distinct parts. And the way to succinctly state this is that delta sub 1 of n is equal to 0 for all n. Next, we have the Rogers-Ramanujan first identity, which says that delta sub 2 of n is equal to 0. Third, we have the Rogers-Ramanujan second identity, which says that delta sub 2 of n is equal to 0. And then finally, we have Schur's identity, which says that delta sub 3 of n is always non-negative. And you'll notice that 3 of these have a superscript of 1. So Alder generalized this idea of the superscript of 1 in 1956 when he conjectured that the difference between little q sub d1 of n and big Q sub d1 of n, so that's delta sub d1 of n, is always non-negative for all n and d greater than 0. And as I said earlier, the Euler and first Rogers-Ramanujan and Schur identities are special cases of Alder's conjecture. So this conjecture was proved over the course of about 50 years. The first major result was from Andrews in 1971, who proved it for d 1 less than a power of 2. Then in 2008, Yi proved a large swath of cases, leaving only finitely many behind, which were proven by Alphys, Jameson, and Lemke-Oliver in 2011, thus concluding the proof of Alder's conjecture. So in 2020, Kang and Park conjectured a generalization of the second Rogers-Ramanujan identity, which you'll recall did not fit neatly into the Alder's conjecture box. To do this, they defined a new function. And notably, they defined big Q sub db dash of n to count the number of partitions of n into parts congruent to plus or minus b mod d plus 3, so the same congruence classes, but they excluded the part d plus 3 minus b, so that's the second largest part. And they came up with a new conjecture. They conjectured that for this new delta function, delta sub d2 dash, which is now the difference between little q d 2 of n and big Q sub d2 dash of n, they conjectured that this was always non-negative for n and d. So they partially proved their conjecture, namely for 2 less than a power of 2 as d, and for even integers n. They showed that their conjecture was in fact true. So here are our project goals. First, we want to prove Kang and Park's conjecture in its entirety. To show you our next goal, we're going to need to define a little bit of notation. Notably, we're going to define big Q sub db dash dash of n as the partitions of n given that the parts are congruent to plus or minus b mod d plus 3, but now where the parts can't equal b or d plus 3 minus b. So that's the two smallest parts in question. And our new conjecture uses this delta sub dA dash dash of n, which is the difference between QdA and QdA dash dash. And we conjecture that this is also always non-negative. So to get to our results, we're going to first need some important theorems that we proved throughout this project. So first is the generalized Andrews lemma. So let S be a set of xi and t be a set of yi such that they're increasing sequences of positive integers with three conditions: that each of the elements of t are divisible by m, that the first element of t is equal to m, and that each of the elements of S are greater than or equal to each of the elements of t. Then it holds that the number of ways to partition a multiple of m into parts from t is always greater than or equal to the number of ways to partition that same multiple of m into parts from S. And this makes intuitive sense because the parts from t are smaller than the parts from S. Next, we proved some important lemmas, which look suspiciously similar to Alder's conjecture. Notably, you'll notice that we're comparing little q sub k1 of m, and this right side looks a little bit different. So we're comparing subscripts of k and k minus 2, and we're comparing superscripts of 1 and 1 dash. So this allows us to somehow modify Alder's conjecture to give us more information about the relation between little q and big Q dash. The way that this was proved was using methods of Yi, and she showed that this little q function was greater than or equal to this little g function, which she defines in her paper. And then using the generalized Andrews lemma, we showed that this little g counting function was always greater than or equal to big Q sub k minus 2 1 dash of m, thus proving lemma 1. Next, we proved lemma 2, which allows us to compare little q sub k and big Q sub k minus 3 dash dash. So again, this looks suspiciously similar to Alder's conjecture, except we have slightly different subscripts of k and k minus 3, and we have superscripts of 1 and 1 dash dash. The proof is precisely the same, where we again use this little g function, and then we use the generalized Andrews lemma to show that this little g function is greater than or equal to big Q sub k minus 3 1 dash dash, thus concluding the proof. So in this project, we proved Kang and Park's conjecture for all but finitely many d. And we're going to walk you through how we went about this using the parity of d and n. So we go through 4 cases, and let's look at the first one. So we consider the first case where d is odd and n is odd. We say that this case is trivial for the following reason. Let's take big Q sub d2 dash of n. Well, by definition, this is the number of ways to partition n, an odd number, into parts congruent to plus or minus 2 mod d plus 3. Now, since d is odd, that means that d plus 3 is even. And since these parts are congruent to plus or minus 2 mod an even number, these parts must all be even. So we're trying to partition an odd number into even parts, which isn't even possible. So therefore, this big Q sub d2 dash of n is equal to 0, and therefore this delta function is trivially non-negative. Great. So now let's take a closer look at case 2, where d is odd and n is even. To do this, we prove the following inequality chain. First, we prove there's a bijection between these two counting functions by dividing the parts of this function by 2. Then we apply lemma 1 because d plus 1 over 2 minus 2 is equal to d minus 3 over 2, which allows us to compare these little q and big Q counting functions. And finally, we construct an injection between these two little q sets, which allows us to conclude the proof and say that Kang and Park's conjecture is in fact true for d odd and n even. Next, we prove the following cases for d even and n even and d even and odd. You'll notice that these inequalities look suspiciously similar to the previous case, so I'll just walk you through the only modifications. First, we have over here that these functions look a little bit different. To compare this function to big Q sub d2 dash of n, we use the generalized Andrews lemma. And then for d even and n odd, we use an injection because we're comparing a partition of n plus 1 to a partition of n. So thus we've concluded the proof of Kang and Park's conjecture for all the finitely many d. So now let's recall our other project goal, which was proving the generalized Kang and Park conjecture. which you'll recall was proving that this delta sub d a dash dash of n function was in fact non-negative. Again, we have a trivial case where d plus 3 is divisible by a and n is not divisible by a. Again, the big Q sub d a dash dash of n function is equal to 0, and therefore the delta function is trivially non-negative. Now we'll be looking at some of our other results towards proving this generalized Khunger-Parkes conjecture. First, we showed that for d plus 3 divisible by a, and for all n, that the delta dash dash function is non-negative. And to show our next result, we need to define r as the largest integer such that 2 to the r minus 2 to the a minus 1 is less than or equal to d. And then we show that for sufficiently large d and sufficiently large n, where d and n are divisible by 2 to the a minus 1, that delta sub d a dash dash is in fact non-negative. So we'll walk you through how we did this. First, we're going to prove theorem 1. This was very similar to proving Khunger-Parkes conjecture with these slick inequality chains. We proved a bijection between these two. We applied lemma 2 here, where we were able to compare little q and big Q dash dash and with these respective subscripts. And then finally, we constructed an injection between these two little q sets. So that allowed us to prove theorem 1 alongside the trivial case. Next, we have theorem 2. To prove theorem 2, we used Andrews and Yee's methods, which were the combinatorial methods in proving Alder's conjecture. So following Andrews, we showed that for any d that's a difference of powers of 2, that we have this inequality chain. Not to worry about what this L function is. All that is it's some sort of partition counting function that comes in handy as an intermediate set. And thus we can show that this inequality chain is true. To prove this next bit, we used Yee's methods and we used Herb bounds to get this long chain of inequality. And these L, K, and G functions are again just some special partition counting functions that allowed us to get that this little q function is greater than this big Q dash dash function, thus proving our result. Finally, we used Alphys, Jameson, and Lemke-Oliver's results to achieve some headway on the remaining finite cases of Khunger-Parkes conjecture. So you'll recall that Alphys, Jameson, and Lemke-Oliver proved the remaining finite cases of Alder's conjecture after Andrews and Yee. They used asymptotics to do this. And so what we did is we generalized our asymptotics. In particular, we found an asymptotic for delta sub d a of n, which has this main term and then this error term, which incidentally contains little q sub d a of n. So what this means then is that as n goes to infinity, this error term vanishes, which means that as a corollary, we can find that the limit as n goes to infinity of delta sub d a dash dash of n is equal to positive infinity, which lends some affirmation that our conjecture is in fact correct based on these asymptotics. So we have these remaining finite cases of Khunger-Parkes conjecture, notably d equals 1 and d is between 3 and 61, and that remains open. And we believe that these asymptotics used by Alphys, Jameson, and Lemke-Oliver are the key to proving these remaining cases. Essentially reduces it to a finite computation where you can use a computer to run through these finite cases and check that we can ensure that this delta sub k 2 dash of n function is in fact non-negative. We would like to thank our advisor, Dr. Holly Swisher, Oregon State for hosting the virtual REU, the NSF for funding the REU, and of course the SUMS organizers for hosting this virtual conference, as well as our audience members for joining us today. Thank you.